Okay. Good afternoon. Welcome to our seminar today. It's a great pleasure to introduce our today's speaker, who is an internal speaker that all of you know very well, Julian Bueno. He has been here for several years. He did his master already in the institute and is at the moment finishing his, finalizing his PhD thesis. Last year he had already introduced part of his thesis, which will be about delay-based reservoir computing and photonic systems. And today he would like to present an extension of that, how you can get to actually multi-node parallel optical reservoirs and doing information processing with it. A collaboration together with Daniel Brunner in FemPSD Institute. We're happy to have you. Looking forward to your seminar.
Thank you very much, Ingo. And well, thank you to all of you for being here today. So yes, as Ingo mentioned, this work that I'm going to present to you today has been in collaboration with people at the FemPSD Institute while I was there for 2 months at the beginning of this year. And I have entitled the presentation towards photonic reservoir computers, implementing and training a large photonic recurrent neural network. As you can see from the title, we have two words, photonic and computers. So this talk is fundamentally going to be about building information processing devices using optical components. Since this is mostly experimental work, I'm glad to put here a picture of the setup that we used. So I have structured the presentation as such. I'm going to do a brief introduction at the beginning, where I'm going to briefly introduce the optical computing and then what information processing techniques we're going to use on our implementation to build our own computer. Then I'm going to go through the implementation of the computer on the different parts, where I'm going to detail what components we use and for what purpose. Then, in the last section, I'm going to show you how this computer performs. And, well, obviously, we're going to finish with some conclusions and words on future research. So, as you probably know, photonics and optics is a very wide technological field, and we can do many, many things with them. But one of the things that we don't actually do nowadays, normally with optic systems, is process information. And it's not like people have not tried to do these things before. I mean, in the 50s, there was the development of semiconductor transistors in electrical component that made the field explode and provide high computational power in the way of nowadays computers. So people tried to develop an optical transistor. And they achieved the optical transistor around the 70s. And with them, in the following years, they built simple optical computers. But in the decade of the 90s, the field halted, and at the end, it stopped. This was mostly because the optical transistor was not a match against the electrical transistor. The electrical transistor was too good at what it does. So people stopped using optical transistors to build computers. But that does not mean that optical systems cannot process information. That just means that maybe optical systems are not the most suitable field to build optical computation based on transistors. And nowadays, we have a variety of methods of optical implementations for information processing devices. We have, for example, on quantum computers, implementation of optical systems to build them, where quantum effects are used. We have the construction of Ising machines made of delay and optical pulses. And these systems can emulate complex network up to even 2,000 nodes. But for today's talk, we are going to use techniques that are neural-inspired. Neural-inspired information processing techniques are techniques that rely on the fundamental ideas on how our neural system may work. I mean, our brains, neural systems, basically, in a fundamental way, are basically neurons, which have nonlinear dynamics, that are heavily interconnected with each other. We have around 100 billion neurons in our brain. They are connected on average to hundreds of other neurons. So it's reasonable to think that if we build a network of nonlinear elements connected with each other, heavily connected with each other, we could perform also information processing. And this is where this kind of techniques come in. Probably the most well-known technique of this kind nowadays is deep neural networks. Deep neural networks have a structure that is like this. You have all the nodes in your system structured in 3 sections: the input layer, the hidden layers, and the output layer. The input layer introduces the information into the system through the nodes, and these connections transmit the information to the first hidden layer. Then these nodes will apply some nonlinear transformation, and through the connections between nodes, the information will flow towards the output layer, where at the end, the state of the output layer will encode the final output of your computer. So at the end, this system is based on nonlinear nodes with connections with a certain strength. That typically are called inner weights. This kind of technique is currently the state-of-the-art technique for example, things like autonomous navigation, diagnosis of certain pathologies from, for example, X-ray scans, and is currently the core technique in the best Go and chess player. But there is a little catch with this, and is that to make this system work so good, you need to find the optimal configuration of weights. You need to find what is the appropriate weight of each one of the connections here. And since this system can have thousands of nodes and even millions of connections, this is going to require a lot of computational resources. But we are going to use a subfield of this, so something similar, which is called reservoir computing. In reservoir computing, you have again the nodes structured in 3 layers. The input layer again introduces information into your system, and then you have the reservoir. The reservoir is made of most of the nonlinear nodes, and they are basically randomly connected with each other. And you even have some recurrent connections in there. The thing is that when you inject information from the input layer to the reservoir, you are projecting the information in a much higher dimensional space, thanks to the nonlinear properties of the nodes. So this, hopefully, will make, for example, classification of information much easier, which will be performed then on the output layer. In this system, again, you have your input weights, then you have your weight inside your reservoir, and you have the output weights from the reservoir to the output layer. In this kind of technique, you only touch the output weights. You feed the connections inside your reservoir, for example, and in your input weights, and for optimization, you only evaluate what are the optimal configuration of output weights. So instead of trying all the configurations of the weights inside your network, you just try new ones on the output layer. This has 2 big implications. One is that the learning, the finding the optimal configuration of weights is much easier than in deep neural networks, and therefore requires much less computational power. Also, the fact that the weights inside your reservoir are fixed once you build it makes easier the construction of hardware to implement this kind of things. Because at the end, you don't need the ability to fine-tune all the weights inside your reservoir. You build it for once, and then you keep it fixed. So you could think of building this thing with optical systems. For example, I said that to build...
In this parallelism you make between reservoir and deep networks, do they really have the same computational power?
No. The performance is worse here, but the training, for example, is much cheaper, let's say. So yes, there is a detrimental performance, exactly. Yes.
So you only fix those ones and you get the same power?
No, there is always a cost on performance, but typically the cost on performance is not is smaller compared to what the cost of.
But it depends also on the task.
Yeah, it will also depend on the task.
Recurrent networks, which you don't have in networks.
Sorry?
You have here recurrent networks, which you don't have in deep learning.
Exactly.
So you have memory.
Exactly.
All things, okay.
Additional, yes. So yes, we could implement. So for example, using the concept of reservoir computing, we could build this kind of systems on optical hardware. As I said, reservoir computing system requires of nonlinear nodes that exhibit nonlinear dynamics. Optics and photonics is filled with components that exhibit the most variety of nonlinear dynamics. We want the speed, computational speed. Optical systems can exhibit dynamics well into the gigahertz, which would mean that we could bring this speed to computation. And a lot of other small benefits, like for example, they are already deeply implemented in technology. But that doesn't mean that it's going to be easy. There are crucial challenges in the way. For example, the implementation of the different parts of a reservoir computer can be very tricky. And also, in this sense, we are dealing with analog computing, which has different challenges compared to the digital computing that we are used to. Currently, there have been several proven hardware implementations of reservoir computing on optical hardware or even hybrid hardware. For example, employing the nonlinear dynamics of semiconductor lasers, also using semiconductor optical amplifiers. And there are also implementations of hybrid optoelectronic implementations that implement, for example, Ikeda type nonlinearities. But the implementation that I'm going to present to you today has two features that are very interesting and very promising comparing to these ones. One is that we are capable of implementing a spatially distributed reservoir with thousands of nonlinear photonic interconnected nodes. The other is that we are achieving much higher coupling because, as I will show you, we require a high coupling. I mean, as I said before, the neurons are heavily interconnected with each other, so a kind of system like this would benefit for a high interconnectivity. And I will show you, and in fact, what we do is the following. Typically, the implementations have the reservoir, so the nodes and the interconnections on the same plane. What we do is we put the reservoir on a plane and we perform the interconnections using the third dimension. Doing this, I will show you how we can obtain high connectivity, not only high connectivity, but connectivity to many nodes simultaneously. So now I'm going to start explaining to you how we are going to implement, how experimentally we implement this optical reservoir computer. And I'm going to start from the reservoir and with the spatial light modulator. The spatial light modulator is a device like this that is used, for example, in astronomy. And this device basically is used, for example, for wavefront correction. This device is made of many little cells, and every cell has an electrical contact with an offset bias that you can change. But every cell has liquid crystal on it. And by changing this offset bias, you change the properties of the liquid crystal. So light that is incident on the spatial light modulator is reflected with some phase shift, but with a spatial pattern. So what we are going to do is use this imprinting of phase shift for our network. This is how we are going to consider our network. As this system, as this device is in a square lattice, we are going to consider each one of the cells of the device as a different node. The spatial light modulator, for its phase shift capabilities, can perform modulation on two ways: phase modulation or polarization modulation. We are going to use the polarization modulation capabilities for our reservoir. One thing is that this is an optical reservoir, so it means that we need light to go through it. This device that I've shown you does not create light, only interacts with light. So for that, we are going to need to bring an external light source into the system. We are going to use a semiconductor laser that is going to emit a constant intensity all the time, and is going to illuminate the SLM, providing with the light for the nodes. This light is going to be single wavelength and linearly polarized. So in this image, I'm going to show you the polarization capabilities first of this device. What we are going to do in this region, we are going to apply a phase shift with the SLM cells, and in the outside, we are going to imprint a different phase shift. But to record this picture, we are going to record it with a CCD camera with a polarization filter in front. So what we're seeing here is that the light from this region, the polarization has been modulated, so it's going to go through the filter. The outside region imprints a polarization modulation, so the light is actually filtered. So you can see two things in the photo. One is that we have a high contrast between the illuminated region and the not illuminated region. The other is that we have a high spatial resolution here, and maybe here is a little difficult, but you could even be able to see the individual cells in the system.
How many do you have, roughly?
30 by 30. In this first implementation, this area is what we are going to actually use for our network. So these cells here compound our network, and is a 30 by 30 lattice.
And the cycle is intentional?
The circle, because here, as I said, we are illuminating with a laser, and the illumination area that we obtain is a circle. So what we... Sorry?
I mean the donut.
There's a donut.
Here.
No.
No, in the first one.
Well, this is aberrations from the optical system and all that, so it's not perfect.
It's not so the light is not homogeneous.
Yeah, the illumination on the lattice is not homogeneous, and I'm going to show you later, for example, what is the impact of this, for example. So, well, we are using the cells inside this area for our network. On the other photo, we are configuring the SLM in the other way around. So the area in the middle is going to be filtered, the area outside is not. So you can see it.
Another question: you cannot change the polarization in each of the nodes. Is it low? I mean,
No.
the resolution of the spatial node is broader. No?
Sorry, you can change the polarization of individual cells here. Yes,
Okay.
exactly.
Okay.
Yes, you can individually address them.
You can really filtering or filtering.
You can, for example, if you have here a cell, you could change it so individually, independently of the others, and you could, for example, change the intensity that you see here
So
with this.
the same, but you can do it.
Okay. So now that we have our nodes and they have light, we are going to give them some nonlinear properties. For that, we are going to use the polarization modulation that our SLM provides, and we are going to use, to make it, we are going to introduce in our system a polarization beam splitter. This device separates light with orthogonal polarization directions. For example, you can see here light that is linearly polarized in both directions. On the outside of the device, some goes in one direction, and the orthogonal one continues through the device. But the thing is that the intensity that goes through this filter, polarization filter, actually follows a trigonometric square relation. So we could use this kind of transformation, which is nonlinear, as the core nonlinearity in our nodes. Now I want to show you how this nonlinear transformation looks in our system. We are going to build this small setup. So we have from up here the illumination light from our external laser, linearly polarized S, bounces on the PBS, illuminates the SLM, and the SLM will reflect it with some phase shift. Then the light that is reflected will have a linearly polarized light with both directions, and the PBS is going to filter them, separate these components in both directions. So only one of them is going to go towards the CCD camera. And we will only record intensity from the P1. If we change the offset bias of the SLM of all the network at the same time, from the minimum to the maximum, which we can do with 8-bit resolution, so from 0 to 255, as we change it, we can record different intensity that is reflected from the SLM. And as we can see, this profile is strongly resembles as a square trigonometric function, which is what we expected, and which is what we are going to use for as the nonlinearity in our network. So now we have the nodes, the nonlinearity, but we need to give them dynamics. To give them dynamics means that the next step, the next state of the nodes, is going to be affected by the past ones. So basically, what we need is to connect what we are recording from the CCD camera to the SLM. But as the resolution of both devices is not the same, we are going to, and you cannot directly actually connect them, you need to put a computer in between, and the computer is only going to do linear mapping to match the resolution of the image recorded by the CCD camera to the one of the SLM. Additionally, the computer is going to update the nodes, the cells on the SLM according to this update rule, where the state of the node, in the next state of the nodes, is going to depend on the actual state times a feedback parameter plus a bias offset. So once we have implemented this, our nodes will have dynamics. And you can let this system run iteratively. Because this is not time continuous, the system is updated by the speed of the computer in this case, and I have to say that this speed is on the order of hertz. So we have to accept that it's a little slow compared to the gigahertz of a semiconductor laser. To show you that this system can exhibit some kind of nonlinear dynamics, I'm showing you this bifurcation diagram. For those who don't know, the bifurcation diagram shows the probability of observing a certain amplitude on the dynamics of a system when you change for a parameter. In this case, the parameter that we're changing is the feedback strength, and then the probability of observing an intensity or amplitude value is on this grayscale, which is logarithmic. We can see that for low feedback strengths, the system mostly exhibits fixed point dynamics, so stable dynamics, and then as you increase this parameter, the dynamics turn more turbulent until we observe chaotic dynamics. Due to the noise, it's difficult to appreciate the exact moment of these transitions, but from this bifurcation diagram, we can see especially two things. One is that, in fact, we are observing some chaotic dynamics, which is what we are going to need for processing in our reservoir computer system. But the other is that we are observing stable situations, stable dynamics. Because typically, in reservoir computing, you put the nodes to work when you are not injecting any information, the reservoir should be on a stable state, and then the information that you are injecting acts as a perturbation that will send your system into a chaotic space. And you are going to use this response to process the information. So this is the bifurcation diagram of one of the nodes only. And we have seen that it holds suitable characteristics for reservoir computing. Now, I'm just showing you the bifurcation diagrams of other nodes in the network. Due to inhomogeneities, for example, on illumination, the bifurcation diagrams of the nodes are not going to be exactly identical. But we can see that more or less in most of the nodes, the transitions are more or less similar. They exhibit for low feedback strengths a stable dynamics, while as we increase the feedback parameter, dynamics become chaotic. So this means that all the nodes could be suitable for reservoir computing. But what is very interesting is that the exact chaotic dynamics of the nodes is different one from each other. They are not exactly the same. They have slightly differences. And this is going to be beneficial because these enrich the high dimensional space we are going to project our information to. So okay, for now I have shown you that we have a network, we have nodes with nonlinear dynamics. Let's add the last ingredient for a reservoir, which is the coupling. To achieve coupling, we're going to use this element, this component, a diffractive optical element. This element is a small element that has some kind of pattern on top of it that imprints some change of light path, and that, for example, typically helps on focusing. And it can have some structure of the order of the wavelength that you are working on, but, for example, could be arbitrary structure on top. We use this component because it has no mobile parts, is passive, highly customizable, but most important, it will allow us to perform all the connections in our network simultaneously at no cost. And even if you increase the number of nodes, this device will provide you already the connectivity for the new nodes, and only with this single component. It's not a very strange component in the sense. I mean, nowadays people use it, for example, to create logos with light, to create this kind of crosses, or even those kind of square lattices. But the DOE that we are going to use for this creates something like this. So imagine, so in this case, we have our DOE creates an image, something similar to that, and more precisely this. Light from one node in our reservoir, for example, when going through the DOE and one image, we will have a point of light in the center, but then some of the light will be diffracted to create points left, right, up, and down of the central point. And the fundamental idea is that here we will have the same node, but above here, for example, we will have the node above in our network. So in fact, the node that is here would send some light to the neighboring node, and therefore we would achieve coupling. And even more, this, what I just explained, would be the case if the light from the reservoir would only go once through the DOE. Every node would send some of the light to the nearest neighbors. What we do is we make the light from the reservoir go twice through the DOE. So then the coupling would go not only to the nearest neighbors, but also to the ones one step further. So just doing this increases the connectivity from 4 nodes to 12 other nodes, further from the nearest neighbors. We put our DOE in place for our experiment. Here is the PBS that I showed you before. So light from the reservoir would go through here, go through the DOE, then would bounce back from the mirror, and then thanks to this lambda quarter retarder waveplane, the light would go downwards towards the camera. To show you that we are achieving coupling, I'm going to show you the coupling matrix in our system. In this coupling matrix, we see how much of the intensity from one node goes to the other nodes in the network. Here we have on the x and the y-axis the node index, but the node index, but we refer the nodes in our lattice, because remember that our network is not they are not in a straight line, but they are in a 30 by 30 lattice. We index our nodes like this. So the first row is 1, 2, 3, 4, 5, etc. Second, 31, 32, 33, 61, 62, 63, etc. So from the coupling matrix, we see that we have these diagonal lines. The central diagonal line is self-coupling. But these parallel lines are the coupling of the nodes towards the ones above and below, as they are separated by 30 indexes. Which means that, for example, the 31 is coupled to 1 and 61. And the second parallel lines here indicate that, for example, the 61 is coupled to the 1, and the 61 is also coupled to the next one that we will have below here. So these 5 parallel diagonal lines indicate that we not only have self-coupling, we have coupling to the nearest neighbors, and we have coupling to one node further in our matrix. So we are achieving with the DOE what we were expecting, but what is interesting also to see is that the coupling is not homogeneous in our network. We don't have the same coupling strength for all the nodes. This will enrich the dynamics on the system, because the different nodes with different nonlinear dynamics will have different coupling schemes to the other ones. And this will further enrich the higher dimensional space. So this last element creates our reservoir. We have implemented the nodes, we have implemented the nonlinear dynamics, and we have implemented the coupling between them. Now, the next piece of the puzzle is the input layer. In this implementation, we make the output layer digitally. For now, we have not done it yet optically. And we do it by changing now the update rule on the nodes on our computer. Now the state of the nodes, the future state, is going to depend on the previous state, but it's going to depend on this part that is basically the input layer. We have an injection gain parameter, we have the input weights, and then we have the information that we are going to process, or that we want to process. The input weights will look like this. This is a 30 by 30 lattice, so we have one input weight for every node in our network. And we chose the values to be homogeneously distributed between 0 and 1.
I don't understand what is n. So what is the control variable here and what is the state variable?
Well, the state variable is n.
Some bias, something is a property of the node. And how do you control it?
Sorry, the one?
So what is n physically?
So, n would be the amplitude, the intensity recorded by the camera normalized to the amplitude range from the camera.
So those devices are controlled by some electrical bias somewhere in the cell, isn't it?
Yes, exactly.
What is the electric bias there?
The electric bias. I mean,
What is the state of the cell and how do you control it?
I mean, the state of the cell is recorded is a value. Is basically a value, normalized value that you can control with heavy resolution from the device, but we change this value by what we record from the camera.
Which is one?
Correct. So basically, you record the value from the camera, but then when we normalize it, we haven't shown here. Yes.
And then
There's this beta n plus 5 was the part that was known by the computer with the feedback.
I mean, this is the part of the feedback.
Yes, and the other.
Beta is what the computer change electrically the valve, the special modulator is in beta.
Yes, the computer is going to change, is going to update the states of the SLM cells according to this rule. And it's going to use this is information obtained from the camera, which will be an intensity measurement of what the camera records from the network.
there is a missing step that probably is within the beta. So you record n from the camera.
Yes.
You send to the computer, make a computation, and
Yes.
then you have an electric signal.
Yes, you have an electric signal to feed.
Where is here?
Well, you have an electric. I mean, you have. Yeah, I mean. Yeah, I mean. But you normalize this with in a dynamical range of the SLM because the value. I mean, the values are. The problem is that the camera, for example, records in a range, and then you have the SLM works in another range, and you need to feed them. You need to make them compatible one with each other. So there are some normalizations here of the amplitude values.
The computer changed the spatial light modulator, the light intensity changes, and when it reaches the camera, have the new value eta n at t plus 1. So it's in the loop, is it beta, all that is in the beta.
Yes, the beta is, for example, the beta is implemented in the computer. It's not something physical. Yeah, well, then when after you have multiplied the measured state, you multiply it by beta, and then you use beta times the past state to update the cells in the spatial light modulator. Exactly.
And then this gamma, omega, input, and I of t, this is the image you want to process.
The information that you want to process, yes. Exactly.
That has omega is the value of the pixel, and then the I is an average intensity.
Yes, I mean, if you would do, I mean, this is done now digitally, but if you would do it optically, let's say, for example, this could be an intensity related to the information that you are working with at that point. And the thing is that the input layer now is implemented digitally and is done and we do it by this, by changing the update rule of the nodes in our network.
This I is like a time, so there are two times.
No, this I, you mean?
No, I is the index of, no, sorry, it's t plus 1. No, it's okay.
Yeah, the sub-index I refers to the index of the nodes.
Yes.
Okay. So, well, now we implement the input layer. So now we have the input weights and we have the information that we want to process. For example, the input weights are chosen like this. This is a 30 by 30 matrix. So we have one input weight for every node. And the values of the input weight are evenly distributed between 0 and 1, randomly chosen. The information that we are going to inject in our system is values of a Mackey glass time series. Mackey glass time series is a system that follows this differential equation, and when you put certain parameters, you can observe chaotic dynamics. This chaotic dynamics looks like this, and as you can see, is some almost periodic large amplitude fluctuations with then some small things going on top of it. We are going to use this chaotic time series to evaluate the performance of our reservoir computer. And we are going to ask our computer to predict what is the next value of this time series. So you inject one value, and the computer must answer with what is going to be the next value. So good. So this is the input layer. The final part of the reservoir computer is the output layer. As I said before, the output layer transforms the response of your reservoir into the final output of your computer. In our case, we are going to implement an output layer that is linear regression that does basically this operation. The final output of your computer, okay, there shouldn't be a knife here, sorry. The final output of your computer is a weighted summation of all the states of all the nodes in your network. So X now are the states of the nodes, so it will be the N of before, but this is the general rule. So the X state of the nodes, each one of them is multiplied by an output weight, and then all of them are summed. So if you want to build an output layer, you need basically now to implement the output weights and then the summation. I'm going to show you first how we implement the output weights. We do so with this device. This is a digital micromirror display. This is a device used in holography, in beam shaping, but is most spreadily used in projection systems, like the one we have up here. This device consists on a two-dimensional lattice of tiny microscopical mirrors with a high reflectivity, and they can tilt. They can tilt to two angles. And this is a diagram of two of them. For example, in this example, the mirrors can tilt to a position of plus 10 degrees or minus 10. We chose this device because you can individually address each one of the mirrors. It's highly reconfigurable, fast also, and also every mirror has the typical size of around 10 micrometers. So you can have high resolution. What we do to implement our output weights here is to encode the output weights value into the tilting angle of the mirrors. Imagine that the light from the reservoir comes from up, and it illuminates the DMD. The rest of the output layer is in this direction. So for example, the light from a node that comes here and hits the mirror that is looking on the opposite direction, the light will get lost and will not contribute to the final output of our computer. In this case, it's like the weight would be 0. In the case that the light hits a mirror that is tilted towards the continuation of the output layer, light will actually contribute to the output of your reservoir computer. So with light, your output weight will be 1. With this scheme, we can implement Boolean output weights. So they can be 0 or 1. Here I'm showing a photo of the DMD that we are using. So it's a photo taken by us, where we have loaded a matrix, a 30 by 30 matrix, where the weights are randomly chosen, 0 or 1. And you can actually see, microscopically see, that we have the area, and we have the tiny little squares, the 30 by 30 lattice, where we have, for example, 2 levels of reflectivity, because some of them are tilted in the other direction and the other are tilted towards us. So you can see how is the DMD in action. The summation is implemented with a lens. The light from the reservoir, once it's reflected through the DMD, then is focused with the lens, and the intensity that we will measure in the point, focusing point, is going to be the output of our reservoir computer. It's going to be the Y up there. We have to say that due to the residual coherence of the illumination light that we are using, this could have detrimental. This residual coherence could have detrimental impact on the performance, but we haven't evaluated how strong is this. So this is the last piece of our implementation. Here I'm showing you the complete experimental setup. We have down here the illumination laser to provide light for our system. Lights go here, shines on our SLM. This light is reflected, going down, single passes the DOE, bounces on the mirror, goes through the DOE again, so we obtain our coupling, and then goes towards our CCD camera. Then the camera is read by the computer and updates the next configuration, the next state of the SLM cells according to what the computer has read and with the information that we are injecting. Then what we do is the light, the PBS, as I said before, splits the light into beams, one going downwards, but the other one that is filtered is the one that we are going to use to illuminate our DMD there. Then the DMD is going to apply the spatial filter, so the output weights, and light is going to be focused and read by the power meter. So this is the complete experimental setup. And we need only one last ingredient to make this actually work, and it's to find the optimal configuration of output weights. For that, we need to implement what is called some learning technique. And we are going to use a version of reinforcement learning. As I said, the goal is to find the optimal output weights configuration. What we do is, in an iterative process, we try new configurations of output weights. If the new configuration works better, we keep it. If it works worse than the best that we have found until now, we discard it and we try something else. So this approach should allow the system to find eventually configurations that are better than just a random one. So I'm going to show you the first results of our system. Here I'm showing how the error on this prediction task evolves as the system learns. We have the learning iteration, so how many new configurations the system tries. And on the y-axis, we have the prediction error. So how good, so the error on prediction, which is measured with the NMSE, normalized mean squared error, which is an error measurement that you want as low as possible. And what we are seeing is that at the beginning, when you use the random configuration of output weights, you have a very high error. But then, as the system learns and tries new configurations, the error goes down, 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 crosses this line, which defines the performance of a linear reservoir, usually used for comparison, goes down and it reaches errors of 0.07. So this shows that the system actually can perform reservoir computing. But since an NMSE value doesn't mean anything, I'm going to show you how the system actually predicts. Here I'm showing in black what would be a perfect answer, and in color what the system is telling us. We can see that in general the system predicts very bad. We have points going down, the oscillations are not well grabbed, and some points more or less work, but it's pretty bad. As the system learns, the predictions become more and more accurate. And at the point, at our best point, we can see that the large fluctuations are very nice graph, and even the small features usually are well predicted.
So this is one step after prediction?
Yes.
And the step is the tau in the Mackie glass, or what is the step?
It's in the integration step.
It's less than the tau.
Yes. Yes. Yes.
But you input to the learning machine, you input the whole series until that point?
No. Well, you sequentially inject. At every step, you inject one point of the series. But if you sequentially inject, for example, 100 points, due to the memory in your system, the system will actually have knowledge of previous points that you injected. So the computation benefit makes use of this memory for better performance.
So the leftmost point there, blue, has a memory of all the former graphs you were showing?
Yes. I mean, in this, typically, well, here we will have many points that we discard, which are called for transient, so the system has not reached more or less a stable state, but so at this point we would have information of what was injected previously. But for example, if you start prediction, for example, here, these points, I'm pretty sure that would show much worse performance due to lack of memory.
So without changing the DMD, you put a series into that, then start
Yes.
and then correctly predict.
Exactly. You keep the DMD fits, you inject the series, the complete series, and then you get the prediction, one prediction.
But
So
DMD has been configured after a long training exercise.
yes, I mean, you inject, for example, 500 points, you evaluate how this configuration of mirrors in the DMD works, and then you have an error. And then you try another configuration of DMD mirrors, and then you evaluate the error again. And you do this 1,000 times.
But these predictions up to 250, that's what you predict? So you predict all the way from 0 to 250, or you... So you don't,
No.
train the system, and then you predict all the
You predict the next point. So for example, I mean, you, for example, inject here and you predict this point here. Then you inject this point here and predict what is going to be the next point.
You retrain the system now?
You retrain the system after injecting the 500 nodes, the 500 input values. Because you inject the 500 values, for every value you have an answer, and then you evaluate the error of all these answers. Then you have the associated error to this configuration of weights. What you do is you change the output weights configuration, and you run the same. You inject the same values, for example, and then you get the response, the answer of the system to these points again, but now with a different configuration of output weights. So then you compare, for example, the both configurations. What is the error associated to both configurations? And you keep, for example, the one that provides the lowest error. Then you grab this configuration, you make some small change, some new configuration, and you inject again the 500 points. You will get a new error.
Yeah, but one strain, how far away can you predict?
Oof.
How far
Okay, this would be multiple step prediction. You would inject, for example, 1 point and say, predict me the next one. 2 steps ahead, 3 steps ahead. Yeah, but then performance would decay.
Of course, yeah.
Yes.
There's a misunderstanding. What he's asking is also it's the same configuration which does the time prediction, one times the prediction at any moment in this time series. So
Yes.
You don't have a different configuration for every time step.
Okay.
It's the same.
You don't move the mirror, you just
No.
re-inject an extra
Right.
piece of signal to ready to follow.
Exactly. So, okay, with this configuration, these results already show that not only the system is capable of performing reservoir computing, as the error is lower than a linear reservoir, but also that the system is capable of learning and improving the weights configuration. So now I'm going to finalize, I'm going to show you what we can, 2 small tricks that we did to boost performance. One is that, if you remember, our network was a square lattice inside a circle of illumination. Now we do is we grab all the nodes illuminated to become our network. This increased the number of nodes from 900 to more than 2,000, and even close to 2,500. So that we have even more than doubled the number of nodes in our network. And the other thing that we do is the following. Until now, all the nodes use the same operation conditions. So it means that they use the same feedback strength, injection strength, and phase offset. What we do is we separate the reservoir into the nodes of the reservoir in two sets, probably the same size. And we make one set work with one set of parameters, and the other set are going to work with a different set of parameters. In practice, what we do is we change the phase offset on the nodes. So roughly half of the network, of the nodes in the network, are going to have a phase offset around here. So they are mostly going to experience the positive slope in the nonlinearity, and the other half of the network is going to have a phase offset. So they are going to mostly experience the negative slope. You could be creative here and put them closer on the linear part. You could put them closer here. You could put them on top of it. You could do many other things. But this is the first approach. And what we see by doing these two things is that the performance, now, even at the beginning of a learning, the performance is basically as good as we did before, after all the learning. And after learning, the error goes down, 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 and reaches values close to 0.01, pretty low. And as we can see here, the prediction, how the prediction is, actually is pretty difficult to differentiate what the difference between the response, the answers of your reservoir computer to the ones that it should really be. So really the prediction is really, really good. So just to summarize, to wrap up everything that we have explained today, I have shown to you an almost full optical implementation of thousands of nonlinear interconnected nodes. We have seen that performance can be very high, providing with very low prediction errors, and this is while we have been using Boolean output weights, which can become a strong limitation for the performance in our system. And we have seen how using a set of nodes with different operating conditions can be so good and beneficial for your system. This doesn't stop here, because there are many things that you could do in this system. You could implement positive rational output weights, so they are not only Boolean. You could implement an optical input layer, so this computer would be full optical as the information is injected optically and comes out optically. You could evaluate other coupling patterns, and most interesting, you could substitute the SLM by some other active optical element, like for example semiconductor lasers, that would bring the nonlinear dynamics of these devices and the gigahertz speed to this computer. I'm sure someday we will see some of these in presentations here, but for now, I'm going to stop, and I'm going to thank all of you for your attention. Thank you very much. I would like to congratulate my collaborators, Supervisor Ingo Fischer and Daniel Brunner, Laurent, Maxime, Luc, Shelley, and everybody else at the Fento for the good time there.
Thank you very much, Julian. There were already some questions during the presentation.
So you used a time series, but is there, what are the interesting things to solve with this kind of machine? Because it's a 2D, one would think of face recognition, character recognition, things like this.
This task that we implemented is more, let's say, an academic task to show that the system is capable of doing something as complicated as predicting chaotic dynamics, which is not trivial. But definitely you could implement this other kind of tasks, like for example, as you say, recognition, for example, or classification of images to do whatever. So you can adapt. This system shows a high flexibility for other tasks. You just have to change, for example, the update rule in this system. But once you would have, the day you have an optical layer, for example, an experimental one, you could send images, for example, imaging on top of the lattice, for example, for these kind of things.
Not whatever. Static images, but this would be particularly interesting for dynamically changing images. that's why it has the advantages compared to deep learning, which excels certainly at static images.
Yeah, there was more the question. So, what is this method is superior for some kind of problem?
Yeah, it presents characteristics more very interesting for this.
There seems to be a bottleneck, which is the computer. Are you planning to remove it?
Yes.
Have you
This,
have a video?
I mean, this is a proof of concept of the optical reservoir, and as I show, but the idea is to remove this SLM, so the computer and these passive components, and use some active system. Like, for example, you could have a lattice of semiconductor laser or SOAS or whatever element that has an autonomous dynamics, and then you would remove completely the camera, you would remove the computer, and the speed of the system, of the reservoir, would be the speed of the dynamics of your system. And this could be then the gigahertz.
You have said not.
In principle, you could already remove it here, because all what the connection between the CCD camera and the SLM does is that you map one linearly on top of the other, just with an amplification factor. This was practically or technically only difficult here because they had different resolutions.
But for example, the coupling mechanisms could be kept there. So this works already. This would work on other reservoirs.
You have said nothing on the learning algorithm. So how do you fit the weights?
The learning.
Are you using standard libraries or what? How do you adapt? Are you changing the weights in time?
I mean, the weights.
Or what is this best weight with change? This routine is the
Yeah, this is just a very high simplification of the learning. I mean, the learning is controlled with the computer that we are using to run our reservoir, and also controls the DMD. So controls the mirror configuration. What we do is basically we have the output weights. We start with random binary weights. We load them into the DMD, into the mirrors, and then we inject all the Marie-Class time series. The computer itself records the intensity values as the answer of the reservoir computer, computes the error, and compares the error that the new configuration, this new configuration that we tried, and compares it with what is the best configuration up until now. Then, at every step, basically what we do is we grab the best configuration of output weights, so the one that gave us the lowest error, and we change one node. We flip one node from 0 to 1, from 1 to 0, from 0 to 1. And then we load it into the DMD. And we repeat this process. Yes.
So
there
are other things, I imagine, just changing blocks, as in genetic algorithms or things like that.
No. How we select, I mean, we have to select which node we change. We do something a little bit more elaborate, but is something additional. I mean, we can go on the details, but I don't think are so relevant.
Is it correct to say that you don't need a complex network configuration because you are using these diffractive elements, so it's just a lattice of coupling that you are creating? It's a regular lattice.
Yeah, you have a lattice, but the connections, for example, are different from one to the other.
So it's a lattice, but it's not uniform.
It's
not
exactly.
Uniform lattice. Okay, not a complex network in this sense.
Yes, and I mean, it's not scale-free, let's say, but you have then the connections that is not only. I mean, in a lattice would typically be nearest neighbors coupling, but then you have coupling to one node further also.
Second neighbors, you mean?
Exactly, to the second.
Okay. And the other thing is the non-linearity really relevant? Because in the second part you were showing that you were using these two family, and you were telling that the spatial light modulator, the beam splitter was used only in the positive slope or negative slope, giving the idea that you are actually only using the linear part around the point.
Well, depending.
Is the non-linearity really important? Or
yes, the linearity is important. It's important because you will have a linear mapping on a high-dimensional space, and performance will be degraded, for example, in that sense.
So you are not working with a small
exactly.
You are spanning.
For example, the feedback, I mean, you feedback here, if you do feedback strength, for example, would be very small, you would be playing on the linear regime, but then you would, if you increase it, for example, you start experimenting this nonlinear part or the parabolic section.
Yeah, I was going to say that the coupling with the diffraction element, you could also make it different, no? You could couple it farther away or something.
Exactly, you could, I mean, the DOEs are, you call the company and they say, I want this or that, and then you could explore many other different configurations, I mean.
If there's no more questions, then we thank Julian once again.
Thank you.
We still have 2 events next week. First, we have a seminar on Tuesday next week by Mariano Siegmann. And then we will have the winter solstice on Wednesday, which starts with the presentation at 1 p.m., but in a different room, in the seminar room next to the main entrance of the building.
Muchas gracias. Thank you. Hostia, claro, es verdad, podría haber puesto un marca a lo mejor. Sí, tienes que darle al botón verde.